All right, so now we're going to talk about this idea of a basis for a topology. And the idea, if you will, is that you want to describe the topology of the space. It's like in terms of some set of open sets, which you then complete. It's like to give you a topology. Okay, so so a standard way of constructing sort of topologies on a space, right, is to start with a collection of open sets. Which obviously include the set itself, X, and the empty set. Okay, and complete this collection by sort of adding sort of arbitrary unions and finite intersections. And then possibly you may have to, it's like, use these newly added open sets. It's like in the construction of, you know, it's like additional open sets as well, okay? Possibly of the newly added set of elements, okay? Until sort of the axioms of a topology are satisfied, okay? So you might want to, instead of considering arbitrary unions and finite intersections of this ever-expanding set of things, right, where you sort of keep adding arbitrary unions and finite intersections, it's like until you don't get any new subsets. What you can imagine doing instead is to only consider you know, arbitrary unions and finite intersections of a collection, it's like of open sets with certain nice properties, okay? And so this is what leads to the idea of a basis, okay? So let me define that for you, and then we'll say a little bit more about it. So the definition of a basis of a topology is as follows, right? So basis of a topology on X, okay, is a collection B of subsets of X such that the following property holds, that for all points X in the point set, okay, there exists some element of this basis such that X is in that basis set, in that basis element, okay? In addition, there is also the property that if X is in the intersection of two of these basis elements, okay, then there has to be some other basis element in the basis set such that X is in this sort of additional basis set, which is contained in the intersection of the two basis elements. Okay, so so the idea, of course, is that this set of open sets has to satisfy certain additional conditions. And you might ask, well, why can't we just do this construction we had before, where we looked at arbitrary unions and finite intersections? It's like, and we sort of just keep adding stuff, right? The advantage, if you will, working with a basis is that here it's like when you took arbitrary unions and finite intersections, it's like you might possibly have to take arbitrary unions and finite intersections of these newly added elements. It's like which you keep augmenting your topology with. All right. Whereas with a basis, right, you are still considering arbitrary unions and finite intersections, but only of the basis elements. Okay, and so that's somehow simplifies your life quite substantially. All right. So anyway, so let's just make that more precise. So then the topology say U that is generated by B consists of all sets U contained in X. Okay, do it again. Okay, such that X in an element U implies that there is a basis element B in this basis set such that X is an element of this basis element which is contained in U. Okay, so you can construct this topology more explicitly, right? So this topology by taking all possible unions of all possible finite intersections of basis elements. Okay, right. And you can check, for example, that if you were looking at the real line, it's like one basis for the topology associated, the standard topology associated with real line is to look at all sort of open intervals, right? Okay. Anyway, so one other thing it's like which happens often, it's like is that you might have a topology, it's like on sort of a big space, and then you have a subspace of that space, and you want to ask to what extent you can inherit the topology of the bigger space on the smaller space, okay? And so this leads to the idea of what is called the subspace topology. All right, so this is subspace topology. Okay, so we often consider subsets. Let's call that Y contained in X, right, of a topological space. X. And we want to consider the topology on X and how it induces the topology on Y. Okay, so let me define for you this idea of a subspace topology. So if X is a topological space, right, and Y is a subset of X, right, then the subspace topology on Y, right, is the collection of sets, collection of okay, so U is going to be an open set in the largest space, and then I'm going to intersect it with Y. All right, so U is in the topology for the big space X. Okay, so what I'm basically saying is that we say that a set in Y is an open set if you can get that set by intersecting an open set in the bigger space X with Y. Okay, so so this is what is called the subspace topology, and it's a very natural way. It's like to induce it's like a topological structure on subspaces of a topological space. Okay, so let me just stop here for now, and then we'll continue in a little bit.